The next speaker is Yichen, who will be talking about degrees of separation.
Okay, well, how do I put it?
Sorry.
Yeah. So, hi everyone. Today I'm glad to present our work on degrees of separation, and that work is done in collaboration with my co-author Aleksander and my advisor Martin. And so let's talk about our system. So our system is a flexible type system for data race prevention. So before diving into the system, maybe first see what is a data race and how we can use type system to prevent them.
Just remove the box on the left.
Okay. Okay. So what is data race? I think everyone here knows, but I'll explain briefly. So a data race happens when mutable state is accessed concurrently by multiple threads, and at least one of them is mutating it. For instance, in the example here, we spawn two threads, so the two bars is basically running two expressions in parallel. It's a hypothetical syntax, and this is two users. The first one try to acquire one item, and second one try to acquire two items. So this is certainly a data race because the non-items is accessed concurrently by these two threads. When such a data race happens, the result of the execution will be non-deterministic. So there can be different results from execution to execution, and there can be undefined behaviors, and there are some important invariants that can be violated. For instance, here we might end up with both users thinking that they have acquired the item, and the remaining item will be negative. So why is data races happening? This is because of aliases. So aliases has been quite a mainstay in a lot of programming languages. As Dimi just said, it can be used to pass values by reference efficiently. And but there are certainly problems because if we have aliases, one part of code can affect the other seemingly unrelated part, even in another thread, like the data races here. So it is like a spooky action at a distance. So people do want to prevent data races, and they can do that dynamically, for instance, via some synchronization mechanisms, or statically, as we will see, using type systems. So previously, a lot of type systems, like mainstream programming languages like C++ or Scala, they doesn't care that much about aliases, and they use aliases a lot. But recently, more and more type systems, they start to paying attention more and more to this problem. For instance, Rust, it supports fearless concurrency, which is its quite famous feature. And if we translate that example directly into Rust, it's the same example. We have a mutable variable that is shared by two threads, and each thread is one user. That will be rejected by Rust because here we are trying to mutate the non-items in the two threads, and each thread will mutably borrow that mutable integer. And in Rust, it is disallowed because you can only, a mutable borrow in its lifetime is a unique reference to that mutable state. So yeah, we do have type systems that can prevent data races. And why do we want a flexible type system to do that? So the main principle of a lot of existing systems is better unaliased than sorry. So for instance, for Rust, it can enforce uniqueness. So in the example we just saw, we create a mutable borrow to the non-items variable in one thread, and in the other thread, we try to do that again, and that will be disallowed. So the mutable variable cannot be aliased by these two threads and cause data races. So what is the problem of it is that so to maintain this uniqueness invariant, Rust not only enforce it on part of the program that can cause data races, but also on the entire program. That is not a bad idea because the uniqueness invariant can offer us much more beyond data races, like compiler optimizations and other memory management optimizations. But this will require entirely a new mindset for programming, because previously we don't have these assumptions about aliases. So this inevitably invalidates some existing programming patterns. For instance, here, this is another Rust example. we have a vector which takes two integers. It's a two-dimensional integer vector. And we have an update function which takes a multiple borrow of a vector and two functions to update these two fields. And in the main function, what we try to do is that we want to increment these two dimensions by one, and at the same time compute the summation of their old two dimensions. And this is a reasonable programming pattern, but of course, Rust won't allow it because basically in the two closures, each of them will multiply borrow the P, and that is disallowed, though they are executed sequentially and no data races can happen. Okay. Oops. I'm clicking the wrong button. So we are kind of at a dilemma here. So we have this old mainstream programming language. We don't care that much about aliases, and we use aliases a lot, and a lot of code is written in them. And we have those new languages which can control aliases, but they come with a completely new set of principles and mindset. So we cannot easily migrate these old code bases and the existing programming languages to use these new techniques. So can there be something in between, which we can maybe enjoy the bright side of both worlds? And so let's set some ideals. So for instance, this is the same example, but again, written in some pseudo Scala. And we are updating this this vector 2 and compute their summation at the same time. And this should be allowed because these two closures are executed sequentially. But this example should be disallowed. And the only difference between these two examples is that the par update function, it will execute two closures to update the pair in parallel. So the two bars, again, is a hypothetical operator which runs two operations in parallel. And this indeed calls the data race, and the type system should reject it. So here's our objective. We want to have a system that is flexible enough to accommodate those programming patterns while aliases are used a lot. But when needed, it is also capable of controlling aliases when data races is really a concern. And if we can do that, then it would make it easier for existing code bases to be migrated to these new systems and enjoy the safe concurrency guarantees. At the same time, the migration cost won't be infeasible. So now we see that flexibility is important, but how can we do that? Maybe let's rethinking these existing mechanisms. Why are they restrictive? For instance, uniqueness. So we think that because they are enforcing some global aliasing in free environment, and here global means that X being unique, it implies that it is not aliased with anything else in the context. But our intuition is that instead of making such a global environment, we can let the user to specify the degrees of separation, which means that what a value or a reference is actually separated from. And by default, that degree can be empty, which means that no alias prevention invariant is enforced, and the type system works the same as before. And when there is really a concern about data races, we can properly specify these separation degrees and reject those programs that cause data races. And to this end, we are proposing a calculus called capture separation calculus, which we short-named as CSC. So how do we do that? First of all, how does this update and par update function we just saw look like in CSC? So it looks like the following. First, the update function is unchanged because it is sequential, it doesn't cause data races, and we don't have to do any code refactoring to make it work in the new system. And for the par update function, as you see, we have some new annotations, those SEP annotations, which specifies what we call separation degrees. And technically, every variable binding in our system have a separation degree, but by default, that's empty. And if that's empty, then the system works as if there's no alias controlling. So actually, we have a prototype implementation which supports separation degree inference. So actually, in practice, you don't have to write out the separation degrees, and in most of times, compilers can infer them for you. So, and what does this annotation mean? So this means that setpf means that G should be separated from both P and F. And what is separation? It is non-interference in CSC. This means that if both F and G is accessing a mutable state, then both of them are just reading. None of them are mutating the mutable state. And here the pavo, it denotes a parallel lit binding, while the binding and the body is evaluated in parallel. So its semantics is a bit like futures. So for instance, if we define a pavo A, which is a result of OP1, and we have, again, we define a normal lit binding B, which is a result of OP2, and return them as a tuple, then it could be understood as defining A as a future, and you go on to execute the body, and when A is really needed, it is awaited. So how does separation? So separation checking is another important device in our system, and it can establish the separation between two sets of variables. It is used in two places. First is the function application. So it ensures that declared separation degree, as we just saw, is actually respected. And the second place is parallel lets, as we just see in the previous slide. It will check that the binding and the body, the variables used by the binding and the body should be separated. And this will statically ensure that there is no interference or data races between the parallel evaluation of the two. And this is the essence of how data race freedom is statically ensured in our calculus. So, and maybe let's see an example on separation checking parallel lets. So this function, it is quite familiar. We just saw its body. So it takes two operations. It runs the two operations in parallel and returns their results as a tuple. And when we are type checking the body, the binding term and the body term, the binding term would be just OP1 being called with empty arguments, and the body term would be the rest of the body of the function. And these two will be separation checked, and this will require that OP1 and OP2 are separated, which is true because we have a separation degree annotated for OP2. And how does it work for function applications? There are two examples. The first one, if we want to, so we first assume that A and B are two distinct mutable integers, so they won't interfere. And if we want to parallelizing the two operations which incrementing A and B respectively, it will work. What happens is that when we type check the first argument, the separation degree is empty, so it succeeds. So it's like no aliasing controlling is happening. And for the second one, we want the separation between A and B, which is true. And for the second example, we want to incrementing A and at the same time reading A, which is indeed a data race, and it will be rejected because type checking the second argument will require the separation between A and A itself, which is not true in our type system. So how does this separation checking actually works? We are using it, but how does it work? So basically, it's symmetric, and once establishing separation between two sets of variables, we will require the pairwise separation between each variable in the two sets. And how does the separation between two variables established? First, it will make use of separation degrees, as we just see. If OP2 is annotated to be separated from OP1, then this can be accepted. And secondly, it will follow aliases. And this implies that our system has some mechanisms for tracking aliases in the type system. And this is capture calculus we just saw in the morning. So its core concept, which is capturing types, it can be used to track aliases. How it works is that so the shape type, it is ordinary type, and the capture set, it predicts the captured variables of the value of that type, and that one can be seen as the aliases returned by the value. For instance, if we have this closure which increments the counter, it will be typed as something capturing counter. We show that it have a reference to the counter. And similarly, for that closure, it will be typed as capturing both counter and sum. And it also shows that what aliases are in that value. So let's go back to separation check and see one more example. Again, we define two mutable variables, and we have two functions incrementing each of them. And the first function is typed as something capturing A, which is exactly saying that it returns an alias to A. And the second one similarly. And the first example, which parallelizing incrementing A and B, it will type check, because when we want to establish the separation between incrementing A and incrementing B, we follow the aliases by looking at the capture set of the type of these two functions, and we see A and B, and that can be separated. And the second one, similarly, will follow alias of increment A, and we see that then we want to establish the separation between A and itself, which fails. And so we have been talking about distinct mutable variables, but how does that work in our formalism? So first of all, we can assume that two freshly allocated mutable variable is separated because a freshly allocated thing is unaliased with anything else in the system. So that assumption is correct. And how is that expressed in our system? Basically, when we declare a new mutable variable in the formalism, we can freely choose its separation degree, and it can possibly spanning over the existing context. For instance, here in this example, we are defining 3 mutable variables in a row, and the first one, it can have an empty separation degree, and the second one, it can be A, and the third one, it can be A and B. So for each of them, it's everything existing in the context. And although these separation degrees, they are asymmetric, but separation checking, it is symmetric. So the separation between any two of these 3 variables can be established in our system. Okay, so actually, we can view alias tracking from a capability-based perspective. How does that work? So capturing types is original purpose for effect checking, and their perspective is capability-based. So the effects, they are performed via program object capabilities, and capabilities, they are just represented as program variables. So tracking the captured capabilities of a closure is to predict what effect that closure performs. So why does that matter? So actually, accessing a piece of mutable state can be viewed as an effect as well. And we can view a mutable variable as a capability to access itself. So for instance, again, this closure, it is incrementing sum, which is some mutable variable by 1, and it captures sum. It can view that it retains the capability sum, which is a capability to access or mutate the mutable variable itself. And so it's returning alias to sum. And why this perspective matters is that if we view a mutable variable as a full capability to access itself, it is really natural to have a capability derived from this full capability to be just the reader capability, which models the read-only access to a mutable variable. And this is how reader capabilities work in our system. For instance, here we have mutable variable A. We derive a reader capability for it, and the parallelizing 2 reads is okay. But if we want to parallelize reading from A and writing to A in parallel, then that will not work. Okay, so we established some formal results for our calculus. And first of all is type soundness via progress and preservation, and the statement is just standard. And secondly, we formally show that our system can prevent data races by showing that the reduction of a well-typed program is confluent. And the confluence statement is also quite standard, and except that we are using the first gray box shows that it is a store equivalence judgment, and we need that because if 2 programs are executed in different orders, in different ways to like interleaving the parallel evaluations, their stores might have different order of bindings, but these 2 stores should be behaviorally equivalent, and this is what is modeled by this judgment. And also this, the second gray box is just means that for this term and this store, there is some typing context that corresponds to this store, that this term is well typed. So a direct corollary of our theorem is that given to terminating reduction of evaluation configuration, if we get 2 answers, A1 and A2, then these 2 answers, they are the same. So the answer of reduction is always unique, although the reduction is, can be interleaved in arbitrary ways and because the parallel late bindings. And in conclusion, we identified, first of all, we identified a dilemma. Well, in data race freedom, so there is a gap. First, on the one side, there is a mainstream type systems, which a lot of code is written, and but they don't care about aliases, and they use aliases a lot. But on the other side, aliases, they are causing data races and other problems. So there are type systems that prevents aliases, but they come with some new principles of aliasing, which requires some shift of programming paradigm. So existing codes, they cannot be easily migrated to these new systems. But if they can, they will benefit a lot from the safe concurrency guarantees. So our system is intended to try to fill this gap, and it follows like a control as you need paradigm by default. With empty separation degrees, everything works the same. And once data races are really a concern, we will do alias prevention. And we have studied its formal properties, its type soundness and confluence. And also, we have a prototype implementation which supports separation degree inference that can reduce users' notational burden. And that's all. Thank you.
Okay, any questions?
So first of all, I have a technical question or a clarification. Could you show me slide 17? So there's a binding there, and you're binding A,
Yes.
you're binding value to A in op1, and then I think you said the body is the whole rest of the function.
Yes.
But the rest of the function uses A, so it seems like it's not separated. What am I missing?
Yes, so it uses the result of A, and but data race will happen during the evaluation of A. So the separation that is actually enforced is like all the variables used by the binding term of A and all the variables used by the body of A except A itself. These two parts are separated.
I see.
Yeah. Because
I see. So
here,
it's unlike a normal parallel block because you're binding something, and then in the body you're going to have to wait whenever you get to that thing.
Yeah, because when you use A, you will await until the evaluation of A, and that won't.
Got it. Okay, thank you. Yeah, that's helpful. So I have a more design question about, I guess, about the previous slide, but about the whole system. So you have inference, which is really cool in terms of avoiding the need to annotate, but it could also be that I might have a harder time understanding, error messages if there aren't annotations in the code. So I wonder, have you seen this to be an issue? Do you have a particular design approach that avoids the kind of problems that people have with inference for standard ML and other similar languages with inference?
Yeah, so for now we don't have real experience because we haven't tested on real-world code basis. But in those small-scale examples, it works fine. And I think if that is a problem, maybe there are some alternatives. We don't do inference by default, but we have some defaults set for each. We have some defaults for these sort of annotations. And one possible default is that. Wait a minute, I want to go back to. Okay, which slide is it? Okay, it's here. Yeah. So one possible default is that when we see the step here, it has to be like separated from all parameters that have been introduced like that, and that might be a possibility. Also, it could also mean that it has to be separated from the body of the function, which is also might be intended by the programmer, but this is quite an ongoing question.
Thanks.
Yeah.
Really cool talk. Cool to see efforts to make this more ergonomic. The thing that I'm curious about is you're comparing to Rust mostly, but then your implementation and it seems like your formalism are more geared towards Scala, which is garbage collected. So Rust, the static semantics prevent not just data races, but also things like use after free, because if you take like exclusive ownership of something, you can destroy it. Do you not have to worry about this because Scala doesn't have a garbage collector, or does have a garbage collector, or do you actually also prevent use after free and similar issues?
So we are not trying to argue that we will replace Rust, but we just want the goal of the objective of our work is just data race freedom. So we won't care too much about those memory management things, and for that part, Rust is really more expressive and powerful than us.
So just to clarify, that means that you, unlike the previous talk, you don't actually prevent undefined behavior. You only prevent data races.
Yeah, only data races.
Okay, thanks.
Any other questions?